Welcome to the Small Unmanned Aircraft Systems for Agriculture Risk and Reward webinar series. This webinar series is supported by 4 faculty, starting with Dr. Mengmeng Gu at Texas A&M AgriLife, Rusty Rumley, staff attorney at the National Agricultural Law Center, Dr. Jo Marie Maha, remote sensor engineer at Clemson University, and Dr. Jim Robbins with the University of Arkansas System Division of Agriculture. The purpose of this session is to provide an overview of sensors. This session is part 5 of a 7-part series. It is important to note that these webinars are partially supported by a grant from the Southern Extension Risk Management Education Center. No endorsement is implied or discrimination intended for firms or references included or excluded from this presentation. This webinar is for educational purposes only and not meant to provide legal or regulatory advice for the safe and legal operation of any small unmanned aircraft system. It is the responsibility of the SUAS user to read, understand, and follow all FAA regulations. Let's get started. Again, simply to mention that this is one webinar of the 7 webinar modules that are included in this series. The webinar team has developed several handouts that are available at the URL on your screen, or contact one of the presenters directly. Remember that there are lots of issues to discuss when dealing with SUAS, and this session will simply provide an overview of the types of sensors used in agriculture. The other topics are covered in one of the other sessions. It is worth noting that there is really nothing new about the sensors that will be used on SUAS. They simply need to be reduced in size and weight for use on these lightweight aircraft. Sensor manufacturers have responded by quickly modifying current sensors to SUAS platforms. This table summarizes the different types or classes of sensors most likely to be used on UAS. The table gives you an example of a brand of sensor and the relative cost, and the far right column gives some examples how each class of sensor might be used. We anticipate that for the majority of agricultural producers, the most likely types of sensors that will be purchased will be standard red, green, blue RGB camera, a modified RGB camera, near-infrared, or multispectral sensor. It is also possible that as improvements are made to thermal sensors, they may be something that is considered. Hyperspectral and LiDAR will likely have very specialized uses based on the sensor cost and the challenge in processing images. Note that the speaker's notes provide links to a number of articles on sensors for agriculture and examples of specific sensors. It is worth mentioning that whether a sensor or any other payload, you must consider the weight and balance before flying. Some aircraft manufacturers give clear guidance on payload capacity, and that must be taken into consideration. Another issue to consider before attaching your sensor is to be aware of any object avoidance sensors should your aircraft include that technology. This is simply an example of a sensor suite, which is likely more common in research where researchers wish to make a direct comparison between different sensors during the same flight. This complex sensor package would not be common for most users. Another helpful hint is to make sure you purchase the appropriate calibration panel for your specific sensor. Calibration is especially critical if you plan to compare observations over time. The big craze right now is RGB cameras that have been modified. So let's delve into that so participants have some understanding why these cameras are so popular. First, we need to review the electromagnetic spectrum. Notice that what we can see, the visible light, is a small section in a broad spectrum of wavelengths. Longer wavelengths just outside the visible spectrum include infrared radiation, which is very important, especially in plant science. There are several subdivisions within the infrared range, and the near-infrared, or NIR, subsection is of particular interest to us. The near-infrared range extends from 750 to 1400 nanometers. Under most conditions, humans cannot see infrared light. Again, we apologize for all of the detail in delving into this topic, but by providing this background, hopefully you will be better prepared for how some of the sensors work and thus better understand some of the processed image products. Let's start with a hypothetical healthy tree on the left side of your screen. Notice the arrows above the tree indicating the percentage of visible and near-infrared wavelengths being received by the plant and the percentages being reflected. Now let's look at a hypothetical tree that is under some kind of stress, whether that is moisture stress, insects, or disease we're not specifying. Pay attention to the shift in reflected wavelengths of near-infrared and visible. We call this spectral shift. For many years, plant scientists have tried to correlate specific components of reflected wavelengths to biophysical plant parameters. Think of this as the holy grail for plant scientists. The literature is full of examples of what we call vegetation indices. This is kind of like pursuing the holy grail to discover the relationship between specific reflected wavelengths and a very specific plant parameter. The vegetation index that receives an overwhelming amount of attention is NDVI, or Normalized Difference Vegetation Index. So we will focus entirely on NDVI, but the same logic will apply to other indices. Just to highlight two indices, the most common index is the Normalized Difference Vegetation Index, or NDVI, which compares two reflected bands, near-infrared and red, using this formula, near-infrared minus red divided by near-infrared plus red. The second example is the VARI index, VARI, which stands for Visible Atmospheric Resistant Index. This index uses three bands, red, green, and blue. We will come back to these two indices in a few minutes. Before going further, it is critical to understand that NDVI or any other vegetation index is not an image by itself, but it is the product of a processed image. Instead of using a large swath of the electromagnetic spectrum, in the case of NDVI, we only deal with two reflected bands, near-infrared and red. Once you have captured an image with a sensor that has acquired at least near-infrared and red bands, we use software to perform thousands potentially millions of calculation that yields a processed image. For NDVI, the simple mathematical relationship is near-infrared minus red divided by near-infrared plus red. The output values range from -1 to +1, which when visualized yields a black and white image. Notice the processed image of a soybean field in the bottom right, which appears black and white. Let's consider another example. This is from Kevin Price at AgPixel. Dr. Price photographed a soybean plant in a greenhouse, and notice there is a section in the top left that is labeled as unhealthy and appears yellow or chlorotic from some unspecified issue. Dr. Price will photograph the same plant with a camera or sensor that includes near-infrared bands and then process that image to produce this false color NDVI image. So what happened to the black and white that we previously mentioned? Most people prefer viewing these images using a color spectrum. So a further step in processing the image is to change hues of black and white to colors. In very general terms with NDVI, we associate pink and red hues with a problem and greens with healthy tissue. But this broad generalization can easily allow you to fall into a trap. This near-infrared photograph taken by Dale Bremer at Kansas State University is of a golf course fairway. The tee is on your right and the putting green is on the far left. Looking down the center of the fairway, I doubt you will see much of a pattern or change. However, when we process this near-infrared image to yield a false color NDVI image, now we begin to see issues that were not seen in the near-infrared or visible image. Focus on the center of the fairway and you will see patches of yellow which suggests possibly some kind of issue that a superintendent needs to investigate. For those that golf, they will immediately realize that those areas reflect the landing zone for a majority of golfers. Golfers will stand in that area, causing compaction, and their second drive to the putting green on the far left will likely cause a divot, which is further damage to the turf. Now focus on the putting green on the far left area of the image. There's a small area at 1 o'clock that is highlighted in red, suggesting a serious issue that needs attention. Look carefully. Notice that the hot red spot is simply an artifact caused by the shade of a tree northeast of that area. Oops. This is the trap that you can fall into if you simply believe that red is bad and green is good without giving any thought to analyzing the overall situation. Many of you will be approached by outside services anxious to sell you these pretty vegetation indices without providing any interpretation on what it means. While the research community is racing to make research-based correlations between plant issues and vegetation indices for specific crops, in most cases we are not there yet. Here's a practical application of NDVI. Again, referring to work by Dr. Dale Bremer at Kansas State University. He exposed turf plots to different levels of water stress and then took a near-infrared image that was processed to give this output. There was a very strong correlation between the colors in the image and the level of water stress. Having explained in painful detail the value of spectral analyses and useful applications, we need to briefly explain the science behind the hugely popular modified RGB cameras. To start with, all digital cameras have a sensor behind the lens that is sensitive to infrared wavelengths along with the visible spectrum. In fact, digital camera sensors are so sensitive to near-infrared that a hot mirror, a filter that lets only visible light pass, is often placed in front of them in order to prevent near-infrared contamination of the visible signal. As a result, a modification of the camera is needed to remove the hot mirror and replace it with either clear glass or a visible blocking filter. For NDVI, we are interested in the near-infrared bands to pass, so we replace the filter with a near-infrared band pass filter. What is so exciting about this is the fact that we can turn a low-cost RGB camera into a low-cost multispectral sensor, bringing affordability to the remote sensing field. The person that first figured this out deserves some kind of award. The photograph on the right shows the back of a GoPro camera removed, revealing the digital sensor and filters in front of the sensor. You can modify your own camera if you wish. Modifying a camera in such a manner is not too difficult, provided you have patience with small connectors and a guide that tells you what to expect at each step. These guides are easily found online. We would encourage most of you to either send your camera off to companies to perform this conversion for you or purchase a camera that has already been modified. A common question that we get is, can I change my camera back to an RGB camera? And the answer is clearly yes. However, imagine that every time you open up your camera, you're likely to introduce dust and run the risk of messing up optics or electronics. We would strongly suggest having a modified and RGB camera. The reason we went so far into the weeds on modified cameras and NDVI is because it is so common to see these products on the market. It is very common to find an aircraft that includes a modified camera that would allow you to generate NDVI images. Remember, NDVI itself is a processed image that requires software. Examples of software to produce NDVI will be discussed in a separate session. When collecting imagery, we have a few helpful hints. First, if you read most remote sensing books, they will tell you to collect images between 10 a.m. and 2 p.m. The reason is to minimize shadows. Next, wind is a major consideration from a flight standpoint and from an imagery standpoint. It is likely obvious that the stronger the wind, the harder it is for your aircraft and sensor system to stay stable, which can reduce the quality of your output imagery. It may be less obvious that if you are taking images of plants on the ground, high winds will disturb the foliage so much that you will get blurry images. Thus, wind, for a variety of reasons, is a consideration before planning your flight. Another helpful hint is to pay attention to the type of lighting, which may play a critical role in your imagery results. The middle weather condition with large, billowy clouds could be a disaster for you in that large patches of shadows may randomly pass through your area of interest. Again, a reminder that the speaker's notes have lots of resources related to remote sensing and sensors. While speaking about sensors, it is an appropriate time to simply introduce the topic of big data. Again, just a helpful hint that if you have never collected aerial imagery before, you need to be prepared for the impressive amounts that you can capture in a short period of time. Aerial imagery data sets can be extremely large, and therefore you need to be prepared for the time and effort to download and process the imagery. Over time, we have had many first-time users come back to us and say, you should have better prepared us for the hardware requirements and time to process these images. I had no idea this would tie up my computer for an entire day. Remember that the intent of this webinar series is to reduce the risks associated with adopting this technology. And having said that, in your financial planning, you need to factor in, do I have adequate computational hardware and software? You will need more than just a $1,000 aircraft. Just as we decided to conduct analysis of the types of features we need when purchasing an aircraft and sensor, we should put pen to paper and evaluate what approach makes best sense for us. One option is to own your own aircraft, sensor, computer, and software. Another option is to own the aircraft and the sensor and yet pay an outside vendor to process your images. And a third option is to simply hire an outside firm to provide everything. Which is the best decision for you? And thanks to Randy Price at LSU Ag Center for this very thought-provoking table. If you do plan to upload images to an outside vendor, you need to also consider what type of internet speed you have. In the university, we are very fortunate to have access to very fast internet speeds. One source where you can test your speed is speedtest.net. Since we already introduced this concept of using outside providers to process your images, be aware that there are many options available to you. One word of caution. The reason we spent so much time giving you a quick overview of NDVI was so you would be better prepared to analyze situations that you will face in the marketplace. In this example, a company was provided with RGB images, and yet they produced an NDVI processed image, having not been provided near-infrared bands. Remember, to be labeled NDVI, you need near-infrared and red bands. If you use RGB bands, there are other indices, but it can't be called NDVI. Remember that a goal of these webinars is to better prepare participants for what they will face so you can reduce your risk and make better informed decisions. If you want to read a thought-provoking analysis of this topic, of the appropriate applications of various vegetation indices, I would encourage you to read the white paper generated by Agrobotics. It should be easy to follow that as our flight altitude increases, our footprint increases, and our resolution decreases. Higher altitude flights capture a larger footprint, however, the resolution decreases. You need to decide what kind of resolution is required. Very high resolution, thus low altitude flights may be necessary to generate 3D models, but not as necessary for a general health assessment. If you plan to stitch multiple images together, you will also need to consider side and front overlap in your flight planning. Fortunately, the newer flight software makes creating these more complex flight plans easier. Much of the new flight planning software allows you an instantaneous comparison of different flight route plans. If you have never stitched an image before, this is one example. A stitched image that has not been cropped is easy to identify by simply looking at the irregular edges, which is a result of the composite images being stitched together. This concludes Part 5 on sensors. We hope this series helps reduce your risk in dealing with drones for agricultural applications.